this particular presentation belongs to the discipline of data science, wherein we build models. So the way it works is, let's say, I've seen an uptick in account takeover fraud for credit cards in the US, let's say. And so obviously I need to do something about it. And one way is to, one way to counter the problem is to build a model wherein, let's say, I'm scoring transactions, or let's say I'm scoring applications, or let's say I'm scoring online activities such as, request to change the communication address and so on and so forth. And in the realm of building models, uh, over the past decade, there's been a significant shift towards using artificial intelligence or machine learning, as we call them. And what has happened is, since computing has become really inexpensive over the years, there's been a very steady shift towards using brute force techniques as far as these algorithms are concerned. So let's say an algorithm that, like neural network, all it does is to sort of get into multiple reiterations wherein you've told the algo that this is how a fraud activity looks like, and then the job of the algo is to sort of find patterns so that it can match to the best extent possible. And a brute force kind of an algo, it sort of incentivizes the data science professional to sort of operate in a garbage in, garbage out kind of framework. Because then what happens is, apparently there's not too much need to understand how the criminal mind works, because all you need to do is to sort of throw your hundreds or thousands of variables at the algo, and then you hope that something magical will happen. So this particular presentation sort of takes a detour from the current process of brute force computing. And what I'm trying to argue over here is a better approach might be using causal AI, wherein what we are trying to achieve over here is, we are trying to find out those features that have a cause and effect relationship to the fraud trend that I'm currently observing. So before I get into details, here are some basics. So what exactly is causality? Causality, of course, is the influence by which an event or a process or an object contributes to another event or a state or an object, where the cause is at least partly responsible for the effect. And obviously, the effect is dependent on the cause. Now, something and in the realm of data science or statistics, the one concept that is the diametric opposite of causality is something that we refer to as spurious correlation. So what that means is, so let's say a favorite example of mine is, we've seen during the months of summer. I'm sorry. What we've seen is there's almost always a positive correlation between ice cream consumption and number of deaths due to drowning in swimming pools. And so that would make so if someone wants to predict, let's say, deaths due to drowning, if you use ice cream consumption as an independent variable, you might get pretty good results. But over there, it's not that ice cream consumption causes someone to drown. There's a confounding variable over here, which is like, which is the weather, or let's say the season. Typically in summer months, more people have ice creams and more people go swimming. So that's why you tend to see a positive correlation between these two apparently unrelated factors. And it would obviously not be wise to sort of use ice cream consumption if you are trying to predict deaths by drowning or vice versa. And another favorite example of mine is, the graph that I've sort of plugged in over here. The number of people who drown by falling into a pool, that correlates with the films Nicolas Cage appeared in over the years. So then again, even though you would see an extremely positive correlation between these two variables, it doesn't make too much of a logical sense to use one to analyze the other. Similarly, if I tie this back to fraud analytics, so let's say I'm at this point of time, I'm seeing a lot of fraud in the segment of credit cards, and let's say these are at jewelry stores, let's say in the city of New York, and let's say the transaction amount is between $5,000 to $10,000, right? So obviously these are certain features that are there in my data set, And if I leverage these features, I would be able to arrive at segments where the fraud rate is really high. And I can then, build solutions accordingly so as to precisely target, those kind of segments. But here again, a feature such as the transaction amount would not be the cause of the trend. It would merely be the symptom of it. If I sort of draw an analogy between fraud trends vis-a-vis, let's say, the medical world. So let's say if someone has a headache, that might be a symptom of the underlying disease. So if you cured the headache, that would be, a very temporary solution. What we need to do is to cure the underlying disease so that the headache or the other symptoms, they don't reappear again. So I'll give you an example of, of a feature that might be a causal feature. So let's say, a while back, many years back, in fact, we were, I was a part of a project wherein, there was a lot of fraud applications or ID theft, that was going on for credit cards. And we found out that, one of the modus operandi was this was going on in we're actually siphoning off the credit card or the driving license details in order to score these kind of credit card applications. Now, when I scanned the data, I found that certain states had a higher fraud rate than others. Here, state means the state a feature in my model or in my solution. But I was aware that, the moment I sort of hard code the states from which I'm currently seeing the uptick in fraud loss, fraudsters would immediately shift to the other states in the country. And as a result of that, the shelf life of my solution relationship I was observing fill up the application form, and when the person actually clicked on submit, and
Looks like we lost you for a minute then, Debanjan. If you want to resume your presentation where you left us off, that would be fantastic. I'll give you a moment to catch back up once again. Really insightful stuff so far. Hopefully, the internet decides to be our friend this time round.
yeah. Let me start again.
No problem at all, sir.
Yeah, sorry for that. So yeah, so I was in the previous slide, I was speaking about spurious correlation, wherein there might be two variables, and apparently you would see a strong correlation, but there's no causality between those two variables. So for example, the graph over here, the number of people who drowned by falling into a pool, this sort of correlates with the films Nicolas Cage appeared in. But that doesn't mean we can use one to focus the other. It doesn't mean that we should be using one of these variables to try and understand the other. And on a similar context, if I do an analogy in the world of fighting fraud, then often what happens is a lot of trends that we see, some of the variables that help us to define those trends, some of them have a cause and effect relationship with the trend, and some of them are mere symptoms. So for example, again, to draw an analogy from the medical world, so let's say if someone has a headache, that would be the symptom, and that would be how the underlying disease is possibly expressing itself. And if I cured the headache by taking a painkiller, that does nothing to cure the patient of the underlying disease, and the headache might again recur tomorrow, right? Similarly, in the world of fraud, let's say I'm trying to build a solution for credit card fraud, and I'm seeing this trend that's on at this point of time at, let's say, jewelry stores in the city of New York, where the transaction amount is between $5,000 and $10,000. So now, there's nothing stopping me from using the state as a variable or the transaction amount bucket as a variable in defining a solution. But the moment I do that, fraudsters would switch and move on to other buckets, because the moment that the card transactions get declined, they would be aware that the organization has placed that kind of a rule. So that this sort of a thought process helps me to separate the cause from the symptoms. And if I'm able to sort of identify those features that have a direct cause and effect relationship to the fraud trend that I'm observing, there are multiple benefits of it. And the primary benefit of it is that the shelf life of my solutions will be longer, because it will be all the more difficult for fraudsters to navigate around my solution and to sort of come up with this different modus operandi. So I'll give you an example. So there was this project that I was a part of many years back, wherein we were trying to build a solution to counter ID theft, and we were trying to score actually incoming credit card applications, and all of these were online applications. And obviously, there were certain states where the fraud rate was really high, and we were wondering whether we should hard code those states as a part of the solution. But we were aware that if we did that, fraudsters would migrate to other states, and the solution would fall flat on its face. So then we came up with, we did a lot of causal engineering in that project, and we came up with subplots that were a part of the story. And one such subplot was a lot of senior folks, who had checked into these daycare homes. They were being the victims of ID theft, wherein the caregivers were actually siphoning off information like, credit card information, driving license information, and so on and so forth, to apply for financial products on behalf of these people. And from my data set, I was aware that what was the start time of of the session, and I was aware of what was the end time of the session, and I could come up with a variable which was like, if someone belongs to the higher spectrum of the age group, and if the duration of the session is ridiculously low, then probably that would be an outlier, and it tells me that someone else might be typing. There might be a younger person who might be typing in the information, and that might be a case of ID theft. So these kind of features, help us to sort of arrive at stories which had a direct cause and effect relationship to the fraud trend that we were observing. And we took a lot of pains to sort of identify these kind of features, so that again the model becomes more robust. And a lot of people ask me that do we really need to spend so much of an effort at the stage of feature selection? Because if you follow traditional statistics, what a lot of people do is they would look for something like the information value, and and maybe put in a hard code cutoff that if the information value is above such and such, then I'm more than happy to include those variables as a part of my model building exercise. But there is the field of fraud detection is really different from other analytics domains, in the sense that there's a lot of there's an evergreen cat and mouse game that continues between the financial organization and the fraudsters. So basically, what I have on this slide is a representation of a sequential game, and this is the parlance of game theory. So you have Sally as a person, and she has two different choices, and if she takes the choice onto her right, and then based on that you have Harry, who again can has the option of choosing these two strategies. And of course the payoffs to Sally and the payoffs to Harry, it's a combination of not just their individual decisions, but what each of them are deciding in conjunction with one another. And this is it's very similar to how the financial crime world operates, and especially how fraud operates. Because what happens is fraudsters typically, they take the first move, as in they commit fraud, and then it shows up on the MIs and dashboards of a banking organization. And then that organization starts building a solution, deploys the solution. The fraudsters get the sense of it because their applications start getting declined, or their credit card transactions start getting declined, and then they move on to other ways of operating. Then the fraud again picks up, and then the organization again they go back to the drawing board and they come up with a fresh solutions, and thus the story continues. Now, this kind of a story is very unique to fraud, and it's very different from any other domain where data science is being used. So say, for example, if someone is using data science in image processing, and let's say you have like really grainy images and you're trying to improve the quality of those images using machine learning, or let's say there's this favorite example of mine wherein in a lot of countries machine learning algorithms are used to infer whether sharks are swimming below the surface, close to the beach. And if the algo sort of, detects these kind of shapes, then, the alarm is sounded off. But it never happens that, the shark modifies its behavior because it realizes that such an algo has been placed and now it needs to, take its game to the next level. And this is how, the world of fraud fighting sort of is really different from any other domain where analytics is used. And that's the reason why it makes sense to sort of have a good grasp of how the cat and mouse game sort of operates in the world of fraud, and accordingly incorporate this kind of a sentiment, or this kind of an intelligence when someone is starting to design, fraud models. And I started off this presentation with speaking about that the current generation of algorithms, be it neural networks or be it some of the unsupervised models, a lot of it are nothing but brute force search, where basically it consists of systematically enumerating all possible candidates for the solution and then checking whether each candidate satisfies the problem statement. So basically, let's say let's say I'm scanning 1 billion transactions, and let's say the fraud rate is 0.0005%. So I'm telling the algo that this is exactly what I'm searching for. Now all the algo needs to tell me is what are the thresholds, or what are the various variables using which I can separate the good from the bad. Causal AI, just to recap, on the other hand, identifies the underlying web of causes of a behavior of an event, and it furnishes critical insights that often simple predictive models they fail to provide. And again, on a concluding note, if someone is interested in learning more about causal AI, then there are two ways to actually go about doing this at a feature engineering point of view. One is the person who's building the model has a very good grasp of the domain. So if often what happens is an organization hires data scientists, but data science as a domain is it's domain agnostic. So that particular person might really not have had a good amount of exposure to how criminals think, and that sort of might be preventing that person from understanding which variables are important and which ones are not. So causal feature engineering means that the person has a good grasp, the person is aware of the intuition, the person is able to step into the shoes of the criminal and basically think like him or her, and starts solving the problem by thinking that okay, if I have to do ID theft today, or if I have to do a fraud transaction on my credit card, how do I go about it? Because I'm aware of these rules and these solutions which my organization has deployed. What are the loopholes in that entire spectrum of solutions that I can exploit, and accordingly sort of arrive at those variables which are important. And the other way to go about doing this is if the data scientist doesn't have the domain knowledge, there are various algorithms, one of them being the Markov blanket. This is, again, there are packages available on Python, and if you use this kind of packages, what it basically does is you can feed the hundreds and thousands of features that you might have in your data sets, and it'll spit out those variables that have a very strong cause and effect relationship to the problem that you're trying to solve. And last but not least, to wrap this up, benefits of causal AI. I've been speaking about the longer shelf life of solutions because it'll be all the more difficult for fraudsters to navigate around your solutions. Hence, your solutions, will tend to be more robust. You can use limited computing resources. So even though computing has become really inexpensive over the years with cloud technology, but often what happens is I've seen in a lot of organizations, some organizations are pretty nascent, or they might not have the budget to leverage cloud technology. And a lot of these organizations, I've seen data scientists being being confined to the computing power of their RAM. And a lot of people think that, oh, okay, if I don't have access to fancy hardware or to cloud computing, I will not be able to build a machine learning algo. That is not the case. All you need to do is to limit the number of iterations that you're asking the algo to do. And one way of limiting that is to do a really good job at the feature engineering stage. And causal feature engineering is one of the ways using which you can limit the number of inputs to your model. And last but not least, again, if you use lesser computing resources, there's an extremely high chance that your solutions will have a very low carbon footprint. Again, a lot of AI tech that's being used these days, especially the brute force AI tech, it uses a lot of resources, and there's a lot of research that's been done on the carbon footprint of the various kind of solutions that industries are using. So then again, if you're very cautious about feeding the right amount of information to the model, then we would be able to sort of build solutions which have a low carbon footprint. That's all from my side.